Hello class, this is Ms. Riggins with today's video on section 5.3, the Fundamental Theorem of Calculus. As you're watching the video and you're writing down notes, especially including important notes about important statements, equations, formulas, graphs, examples, things of that sort, feel free to pause, rewind, or replay the video as often as you need so you can get a full understanding of what's going on in the video. When you have concluded watching the video, write down a brief summary about what occurred in the video in your notes and submit that summary as well as a top question via the online WIX the day before class, ideally. All right, let's begin. So if you recall last video, we were talking about the area of a function under between the x-axis and the function on a set interval. And we said that a way to determine that value is to find the limit of a whole bunch of sums, and we call them Riemann sums. But this symbol here represents the exact area between the function and the x-axis on the interval from a to b. And we can approximate this using a certain set number of sums of the function f of x multiplied by the small difference of x. And we don't always have to use x. In our case, we used an example involving time as well. But what this symbol represents is a multiplication of two things: the units of the function here and the units of the independent variable. So we're multiplying these two values together, and that's important to note because that will is a good way of error checking to make sure you end up with an answer that makes sense. All right, so let's take a look. This symbol right here represents the area under the curve of f of t, where between time equals a and time equals b, and that area under the curve and the x-axis between those two things, okay? But if we take a look at that, if you remember, we let v represent the velocity function, so f of t really is a velocity function, and when we're trying to find the area under the velocity function curve and between the x-axis, we really are trying to find the change in position from time is equal to a to time is equal to b. So another way to look at this answer, besides being the exact area between the function value and the x-axis on the interval from a to b, is to look at this as the difference between the function value, the position function for time equals a and time equals b. So in other words, what we're saying is that this answer right here, if f of t is a velocity function, can also be determined by taking the position function and determining the change in position from time equals a to time equals b. And we can determine that if we know what the position function is. So let's say the position function is a function, we're going to call it big F. And big F is a position function and such that the derivative of big F is little f. And in this case, the derivative of the position function is the velocity function. So really, when we're talking about the change in position from time equals a to time equals b, we can represent that by the difference from f of b and f of a, where a and b are the endpoints. And another way to look at that is this notation, which is take the big F function, which is a position function in our example, and evaluate it at a and evaluate it at b and take the difference. And that's exactly what another way we can use to determine what this symbol represents. And besides the area between the curve little f of t and the x-axis from a to b, it also can represent the change in position where from big F to little, for big F from a to b, okay? And that essentially is the first fundamental theorem of calculus. They say the fundamental theorem of calculus, but there's others. So this is the first fundamental theorem of calculus. And the conditions to be able to use the first fundamental theorem of calculus is that first of all, the little f function has to be continuous on the interval, closed interval from a to b, and that the little f function is the derivative of a big F function. And so what the first fundamental theorem says that we can compute this by taking the difference of the big F function at the endpoints. And that's important to understand. Now, if you recall, what we did last video is that we had some interval from A to B, and we broke up that interval into little subintervals of the same length for time. We called each one delta t as far as the distance between each two values. And then we looked at the change in position. We looked at the change in the function over that interval. So let's say that the change in the function can be, the big function, position function, can be denoted as delta f. Well, what does delta f represent? Delta f represents approximately the rate of change of f, the big function, position function, times the time elapsed, i.e. the delta t. Okay, so delta f is approximately equal to the rate of change of the position function times the time elapsed. Well, for very, very small delta t, then the rate of change of f looks very much like the slope of the tangent line of the function at f. In other words, it looks very much like the first derivative of big F at that point. In this case, for the first interval, delta f is equal to the first derivative of f at t naught times delta t, time elapsed. For the second interval, which is t1 to t2, delta f is going to be approximately equal to the first derivative of big F at t1 times delta t. And we can go on and on and on like that until the very end, which could be the last interval. In this case, we're working with just the left-hand rectangles. We could very easily have used the right-hand rectangles. We just had to pick one just to show you this example. So delta F here is approximately equal, based off the rate of change times time elapsed, as the first derivative of the function at n minus 2 times delta t. Okay, and if we were to add all of these delta f's up, we would end up with the total change in position, or delta, or big F, from A to B, because all we had to do is just add those up. And that's essentially the same thing as the summation of the delta f's for each of the subintervals, which can be computed approximately by multiplying the first derivative of the function big F at each subinterval endpoint and multiply it times t. Okay. So basically, all the first fundamental theorem tells us, and this is very, very, very important, is that if you're trying to find the definite integral of a rate of change function, you can compute that by basically determining the total change of the original function. So finding the definite integral of a rate of change function is the same thing as finding the difference in the endpoints function value, okay? Where the rate of change function, moving on, sorry. Okay, so very quickly, I want to address this, which is, let's say I want to find the total distance traveled over this function of the interval from A to B. And some of you ask, well, what if part of the graph is underneath the x-axis? Well, to find the total distance traveled, and distance is a positive value, all I have to do is basically add up the areas. In this case, all the areas are positive because area is a positive quantity. But if I wanted to look at the total change in distance, then that's something different. And in order to determine the total change in difference, I take a look at the last distance value and subtract that from the first distance value. And a way that I can compute this using the first fundamental theorem of calculus is by basically taking this area, adding the positive areas, and subtracting the areas that were underneath the curve, underneath the x-axis. So I just want to go over that. All right, so now let's look at an example. And so that's why this video is a little bit longer, because we're going to use the Inspire, and I'm going to show you an example. So let's say a student is on the 3rd floor dormitory window, which is 32 feet off the ground, and tosses a water balloon straight up in the air with an initial velocity of 16 feet per second. And it turns out that I have an equation for the instantaneous velocity of the water balloon given by this velocity function. Okay, so this is our velocity, instantaneous velocity function for a time t, where v is measured in feet per second and t is measured in seconds. So I have 3 things that I would like to do. I want to, if I let s represent the height of the water balloon above the ground at time t, can I come up with a formula for s of t? And then I'd like to use that formula to compute the differences for different subintervals of the time, and then determine what is the total vertical distance traveled by the water balloon from the time it's tossed to the time it lands. Okay, and so all of that depends on the formula for the height, which i.e. is like the position function. Well, since the derivative of the position function is the velocity function, I have to come up with a way to represent the position function using what I know about the velocity function. So I look at this first term right here, and this first term is negative 32t. So since that's the derivative of something, then the original part must have been a t squared. So I know that the derivative of t squared is 2t. So since this is negative 32t, it seems like the first part of that position function would be negative 16t squared, because when I take the derivative of this, I get negative 32t. And since this part is 16, that means that the original part of the original position function should have been involving just t. And so I end up with this part. And that would seem to be enough, but if you remember that when the student first threw the water balloon straight up in the air, the original height, the initial height was 32 feet. And if the initial height is 32 feet, then that means when I plug in 0 into this function, I should get out 32. So since the zeros will apply, that means I would need to include this. So this is my position function. If I were to take the derivative of this function, I would get exactly this velocity function. And when I would take a look at the initial time of 0, I would get out 32 feet. Okay, so we're going to calculate these values using the handheld. I'm going to show you a trick. Okay, so we're going to we can go to a scratch pad. It doesn't matter, but we're going to use the define function. So I'm going to you can either type the word define, or you can go to actions and do define. And the function, I'm going to call it s, and you can call it anything. So I'm going to call it, let's call it POS for position. I'm going to put parentheses, and I wanted to input a variable t, and that is equal to, if you recall, negative 16, actually let me be exactly, negative 16 times t squared. All right, got plus 16t plus 32. Okay, and I press enter, and it says done to indicate that it's okay. And if I want to evaluate the position at time 0, I input 0 and I get out my answer. So a way to determine, if you recall, we're trying to calculate position function at 1/2 and at 0. So all I have to do is do position, POS, and 1/2 minus POS. And if you notice, it turns to solid, which indicates it recognizes the value. And I get my values here. Okay, so this is just a shorter way of doing this problem. And I can use that to determine the values, for all of these. In the interest of time, I'm not going to do that. And they want to know, what is the total vertical distance traveled by the water balloon from the time it is tossed until the time it lands? So first we have to determine at what time will it land. And it will land when the position function is 0. And as you can see here, being that it's a quadratic function, we can solve this quadratic function and to get our answer. So using simple algebra, we write this function into intercept form, and we see that the position function is 0 when time is -1 or when time is 2. So that must mean that this answer that we calculated earlier, s of 2 minus s of 0, will give us the total distance traveled. And to determine that, we just plug that into our calculator, position of 2 minus POS of 0, and we get negative 32, but which represents that they went down 32 total feet. Sorry.